ladies and gentlemen, and welcome to our final third part of linear models. As you can see on this title, we will focus on splines. How and why, we'll see in a moment. So, generally what we already know is that we have kind of formulate the regression problem with a design matrix. So, our original model formulation focused on that mean of normal distribution that represents our knowledge about the outcomes is a function of predictors, usually linear function of predictors. And there is no problem of adding more predictors or functions of predictors just by adding more coefficients. Beta, which will be a vector, and multiplying it by appropriate vector of predictors, or the functions, values, at the point I, corresponding to the measurement outcome I. So this, of course, can be represented in a vector matrix notation form, which should be obvious to you from any algebra course. So our vector of outcomes, that's why it's bolded, is distributed as normal distribution, or a vector of normal distribution in a sense, with means, which also should be bolded, but later has difficulties with such things, especially on such version like in Keynote, which will be added by a vector of alphas of intercepts, which will be the same, and design matrix times the vector of coefficients of predictors located in the design matrix. And what really can we put into this design matrix? We can put any complication of regression that we really want. We can use multiple predictors. This is not something that we'll be discussing here because it's kind of time constraints of ending semester blocking us here. This is great. There's a great materials available online. I will provide you with my lectures from last year, from slides for those lectures, and also I strongly recommend you to some videos by Richard McElrath, which are available from his website and also on YouTube, and they will cover this aspect. We have already used polynomials, so we can add functions of predictors, but polynomials have many problems. Polynomials can get strange values, polynomials are non-local, so one of the options that we can use as a functions of predictors in our design matrix are B-splines. B-splines, or in other words, base splines, are special functions. These are functions that are so-called functions on a compact support. So those functions are defined on a certain interval, and outside of that interval they are zero. And B-splines, so base splines, are usually polynomials, or something very similar to polynomials, that is defined in certain intervals. Depending on the order of the polynomial, they can be defined on short intervals or intervals requiring multiple points. As you can see, they are defined on certain interval, and then outside of it are zero. What is more interesting is that increasing the order of B-splines, so adding more points over which they are spread, they are becoming more and more smooth. So using multiple points, depending on how many points we are defining in our interval, then our B-splines are the functions that are taking values in those points and are continuous functions elsewhere. So having, for example, 4 knots, so that's so-called the points in the interval, we can assign between them one function of third order that will be 0 outside. What is important about B-splines is that while they are taking only values in non-zero values in certain intervals, they are defined over the entire range, which will be important for us later. So What do they want to do with those knots? They are defining how the orders of polynomials are selected. That's one thing. And for example, if we take a third order spline, so we want to find a function that is a third order polynomial in an interval and 0 outside of it, we need to be located at 4 knots. There will be like non-zero values of those knots, or 0 at the edges. And what is important, that knots can, when defining a spline, can be multiple or can be distinct. If all of them are distinct, then our spline is smooth up to the order of n minus 2. So, for example, a third order spline will be once differentiable on the entire interval. That means that its derivative at the edges are smooth enough that they are fitting into the constant 0. If they're lower order, there are some more problems. If the knots are multiplied, then the their smoothness is lost. So we'll see it in a moment in examples. So what we really want to do here is that we take an interval, we divide it into knots. It's going to be similar to interpolation nodes of some points in this interval. And we want to select functions that will allow us coverage of this entire interval. Usually it's this way that we create series of functions, for example third order functions, which we locate every moving one knot by another by another. In this way, for each knot, multiple but finite, like for example 4 B-spline functions, take non-zero values in them. Because of that, we will be able to reconstruct any function, at least approximate it. Because the idea is that our function will be approximated by a sum of weights, which will be real numbers, and B-splines. So having functions that are varying values in these points, we'll be able to approximate our function, which is the nice property of B-splines is that because all of them are differentiable, at least if they are not at the edges, then of the interval, then their sum is also differentiable. So we'll be able to create a function that is differentiable for further order polynomials once at least, so relatively smooth, and this function will be approximating our target. This is a linear combination, or in other words, look at it as this is a sum of certain predictors, because this is very similar to regression. If we put right points if we want to fit our points at xi, then we'll just substitute for x, we'll substitute our values we are interested in. Nodes are used for specification of functions b1, b2, etc. However, their values are defined in all the points that we are interested in our predictive performance. So the issue that is how to select the knots, because as we can assume, because knots are varying over the entire knots are defining our polynomials. If they are changing, their functions also will change, so our approximation will change. If we have there is multiple ideas how to do it, but if our dataset consists of uniformly distributed samples of predictors, and we want to create a regression that will construct a function as a spline approximant, then we need to see out the data. If our data is evenly sampled over the entire interval, so we have relatively the same number of samples for each of the points that we have here, we can put uniformly, we can distribute knots uniformly and everything is okay. However, if we have points, areas of greater concentration of samples, we have to do something about it. One of the rule of the thumb that is rule of the thumb is to locate the knots at quantiles of the samples. So we take a vector of x values, we compute quantiles of that vector, the number of quantiles depending on the number of knots we want to use, and then they will be located in such a way that they will be denser in the points where you have more data points. If you have RBS where you have less data points, then you should put less movement between splines is possible, because the more splines you have located, the more variance in the function you can observe. And why generally we would like to do B-spline approximation and not, for example, polynomials? Generally, it all depends what we want to do. If our functions are very regular, we know that are very regular, splines are a bad idea, because splines introduce this limitation of finite differentiability. Our splines will always have limits of the smoothness. The first derivative, maybe second if we go higher order, not much more. If we construct a polynomial approximation on the entire interval, we will have infinite time differentiability, which can be very, very useful in certain aspects. However, splines can capture local behavior. So, for example, if we have a time series with a fault occurrence inside it, we could use splines to help us locate that fault, because we'll be able to determine that something is in areas in these nodes. In this area, for these splines, they are, for example, larger or differing from the others. So we'll be able to extract certain information from the behavior of the splines. Moreover, splines give certain potential for numerical efficiency, because if we will try to go to construct more advanced, either non-parametric or parametric models of functions, when creating the design matrices, splines will give us matrices that have a lot of zeros, which can be very, very useful for numerical computation. Not necessarily in Stan, because Stan is not optimized for sparse computation. However, it can be useful for the functions. It can be useful in certain large problems when we have a lot of data and we want to have a lot of base functions or complicated function. Then using the sparsity might be very efficient way to do so. And generally, splines are a special case of Gaussian processes. Gaussian processes are a method of non-parametric modeling of nonlinear relationships, and you can define a Gaussian process that will result you in a spline approximant. However, again, these numerical advantages might be more useful in some cases. Creation of design matrix is relatively simple, because, as we said before, we reconstruct our me vectors for our normal distribution, as with creating a design matrix for each point, and we just take values from base functions at appropriate values of the predictors, because our base functions will be functions of predictor. We are representing the relationship between predictor and the outcome as a function that is a combination of B-spline functions. So, having data points y, I, and data points, predictor values, we can construct the design matrix that will, for appropriate values of predictors, will record appropriate values of all of the B-spline functions. And to do so, we will be, as you can see, this matrix might be large, depending on the number of base functions that we are using and the number of points we are using. It can be a large matrix, but again, because B-spline functions behave as they behave, a lot of it will be zeros. And we will use this this technique for modeling of a very long time dataset, the dataset spanning over 1,000 years, which is the cherry tree blossoming in Japan. This is the traditional it's a tradition of flower viewing, which is that people observe at what time in the year the cherry trees are blossoming, and this data were recorded over. Data was recorded by many years. It was reconstructed from ancient texts, and is available as a data set of 1,000-year samples. So we will see into this data set, and we'll create a spline regression to try to recover the trend of which day of the year it was the cherries were blossoming. So let's move to our notebook. We have standard procedures. We are importing the standard packages. We have the what we usually use. We have two extra things that we weren't using in the previous one. First of all, from SciPy interpolate, we are importing B-spline because we will use it to create the design matrix. And from datetime, we'll import the datetime class because that will allow us to do some for more nicer labeling of plots with the day of the month. So what do we have here? We have our data set that we also took from the Richard McElrath's GitHub repository for statistical rethinking second edition, and we've read that CSV. This CSV is in our memory. We can as a data frame. Let's investigate this data frame. We have 1,215 years, spanning from 801 to 2015. However, we have day of the year when the cherry blossoming occurred, and these data points we only have for 827 years. Also, we have information regarding temperature of that year, so this is something that we can maybe analyze later. So what we will do, we'll just now focus on relationship between year and date or day of the year where the cherry blossoming occurred, and so we will just drop all the rows that does not contain information about date of the year. So we won't be going through our standard procedure of prior predictive checks because generally it might be too much of information at this moment. You are free to check it by yourself. If you have any questions, you can ask me and I'll address it in the next Q&A. Either way, what do we have? We have our model, which is generally the same as our model that we've used before for the model of heights, but with multiple predictors. We have our design metrics, we have measurements, we want to fit, we have a transport parameters for means for each parameters, and we get the priors. For our priors, observing from the data, as we have seen here, we could assign that the fixed term, because we have a constant term in the approximation, should be somewhere around 100, so we can put it here just as some kind of information, because like generally we can assume when the cherries will blossom, and they will blossom in the spring, and spring would be around March, April, so 100th day of the year is like around 10th of the April, so this is a relatively reasonable date. So along with the standard deviation of 10, we get like a good spread here. Then we have we assigned the for our standard deviation, we assign exponential distribution, which is again give us the spread of additional few days, one way or another, with not so thin tails, so some varying is possible. And for our beta coefficients, we just put normal distribution with 0 up to 10. B-spline functions are constrained between 0 and 1, so putting them, multiplying them by variables that allow us relative ease of movement between -20 and +20 will give us very good ability to vary our dates here. So we can of course compile our model, and let's start with defining the splines. So here we have two control variables, spline order, which will start with 1, because will be so-called linear splines, which are not a real linear function, but are those nice pyramids that we've seen on slide before. And we'll start with 5 knots. Those 5 knots we'll just put some points here. We compute those knots by computing quantiles from our data about years. So we have samples which years we had results, and we get those which quantiles. We just divide the 0-1 interval into the number of knots points. So we have new 5 knots that are located at appropriate quantiles. Then we need to handle the edge behavior. That's why we need to add to our knots additional points that will be multiplicities of our knots at the edges. For the for the first order splines, we need to add 1 extra. So it says for higher order, we'll need to add the number of orders. So as you can see, we are adding at the both ends of the knot list. We are adding, we are repeating the edge values with spline order times. So we create the B-spline functions. Usually B-spline functions are created as the one function. So we provide it with weights and it computes a sum from us. However, B-spline class allow us also to provide it with a matrix argument. So our matrix will be the sum of our class will just use vector weights for each of the knots, because they use vector weights which are orthogonal, because this is an identity matrix of appropriate size. Then our splines will be generated as a columns of new matrix. Our result will be a matrix which will have spline values for each of those. So we will get the values which we will compute at appropriate year values. So we will have a matrix that will be filled by each of the columns will be one B-spline function. So this is the most advanced here, and we will plot our base functions how they look here. And for our spline order of 1, we get and 5 knots, we get such functions. So our approximating functions will be created as a functions that are one starts at 1. So these are the edge functions, which I mentioned before, that have a doubled note here. So you have here and here is 0. The same is from the other hand. Not number 5 is 2015, which is also have to be repeated to create a function that goes like this. And then you have those pyramids that are belonging to the knots that we have here. So it has value at the middle knot and vanishes on the neighboring knots. So for the second one is here. Generally, we have less data for the earlier years. So that's why for the more modern times we have more denser splines, and for the earlier years we have less of the functions. We can generate fit our model providing with appropriate data. So we can just provide as n we'll get number of rows, as k we get number of columns of design matrix, provide to design matrix, and we provide it with values of day of the year that we're interested in. And performing a fit here, we get the values of our coefficients for our functions. So we'll get them we'll get them here, and those coefficients will read. We can then sum by appropriate computation, and we can get the. First of all, we can use our mean values, which we saved here, and we can see how the mean of the regression models behave. So as you can see, it can capture the changes here. Especially, it can capture, for example, a trend in the last 2 centuries of moving downwards, and can split the behavior of earlier years and later years with the our functions. And of course, we can consider the uncertainty of our prediction. So generally, what we are doing here is not differing much from what we've done before. We just have more predictors which were procedurally generated, and their behavior is local. So we can see where we can capture certain, for example, kinks in the function that would not happen otherwise. We can, of course, change our spline parameters. We can go, for example, for third order splines, which are much smoother. But again, you see that there's a problem of going with higher order, that the first order spline will have a discontinuity at the edge. The second order spline will have the first spline will have a discontinuity. The second one will not be differentiable here because it goes to 0 as rather abruptly, and then you have the differentiability because now you have enough knots to cover everything what you need. So, and of course you don't reach the values of knots, but you see that all those functions are taking non-zero values at each of these knots. We did exactly the same as previously. We provided with the data set. You see the computation takes a bit more time because the higher order functions require more computation. And then you go with, we can compute some summary, so we can see how the standard deviations of the functions behave. So we have generally standard deviation on the same level of all the coefficients, with extra standard deviation of the entire predictor. And we go with computing a model. You see this prediction is smoother. This prediction is smoother and captures some kind of trends earlier. And of course, looking at the prediction of uncertainty, it can capture a bit more. But of course, we can increase number of spline functions, for example, to 15. These will get, as you see, lesser density where we have lesser data. Then when we have more reliable data, it becomes more and more uniform here. So they are being located here. And of course, we provide our model with the data. Here you can see, well, this is a bit of change for our model because we provided our model with a lot more columns of our design matrix, because we have 15 base functions, but it still needed 11 seconds per each Markov chain, so it's not that bad. And we're getting our summary. We can see here that we generally have our coefficients of our functions, and they have the standard deviations around 2 or 3. Their confidence intervals are kind of some of uncertainty, especially some of them that are really, we are not sure, is it the positive or negative sign, because both of them are really possible. In such cases, some of the intervals are more fixed on what we're supposed to do. And we get this more wiggly approximation here, which of course can be again extended to get the prediction uncertainty and capturing more data. And really, this what you hear is always we've created a model that can capture some kind of local behavior here. The problem is, of course, how to choose right order of functions. Here is the problem that we may risk some overfitting. There is no good automatic procedure for selecting the number of base functions or number of nodes, because this is a discrete variable which are generally ill-fitted in context of of Monte Carlo computation. So it will be very problematic in order to get to estimate the optimal number of knots. We can support ourselves with some kind of cross-validation methods or information criteria, but that will be something that we'll be returning to later. Either way, this example here we did is not really to express some kind of information, but to show you the technique that you can use, really create a very complicated model that can be very good for predictions based on creating the spline approximation. Of course, spline approximations are not extendable, but they can be used for something else. You can, for example, use them in modeling or optimization or something like that. You shouldn't use them as a way of extending them, because you have actually relative reasonability only in their domains of existence. Outside of them, spline functions are not good thing to use. So that is, and this is what we discuss. Here we finish the linear regression part. As you can see, linear models can handle multiple predictors. They can handle functions of predictors. They are relatively simple. We can use complicated functions. You can use simple functions. When you use splines, you are able to, for example, capture the non-local behavior, local behavior, or some kind of varying trends, and you can use it, for example, to study different relationships. So thank you for listening, and that will be the end of the linear model parts. Next time we'll probably handle generalized linear models instead, and how to fit them, which we kind of started before, but maybe we'll put some more focus on that in order to get some better understanding. Of course, all the questions are welcome in the comments or through messages, and if there are some of them if some number accumulates, I will create another Q&A video. Having that, thank you for listening, and